This is part 5 of our videos, Standard Free Energy Change. Free energy is our third factor we need to take into consideration with thermodynamics. So we've talked about enthalpy, which is your heat content of the system. We've talked about entropy, which is the disorder in the system. And now we're looking at our standard free energy change. Delta G, with a little zero up here, means standard free energy change, is the change in free energy, that's the energy available to do useful work in the system. It's the change in free energy that will occur if the reactants in their standard states are converted to the products in their standard states. You cannot measure the standard free energy change directly, however. The more negative the value for delta G, the farther to the right the reaction will proceed in order to achieve equilibrium. As we just finished up with equilibrium, remember if it lies farther to the right, that's towards the products. So the more negative delta G is, the more likely it is to be favoring your products. Remember that equilibrium represents the lowest possible free energy position for a reaction. Now, the lowest possible free energy position is good. Remember, reactions tend to want to proceed towards equilibrium. That is very stable. This represents a very stable condition. We can calculate free energy a couple of different ways. There's 3 methods. The first method is by using this formula that takes into account your standard enthalpy and your standard entropy as well, and the temperature. So we will again work some of these problems with this formula after break, but the formula is delta G at standard conditions is equal to delta H, the change in the enthalpy at standard conditions, minus the temperature in Kelvin times the change in entropy at standard conditions. So delta G is equal to delta H minus T delta S. The second method you can use to calculate free energy is Hess's law. We can use Hess's law with all 3 of these thermodynamic quantities, with enthalpy, entropy, and the free energy. You just would use your values off of your thermodynamic table. You would arrange your reactions so that they cancel out and give you the overall chemical reaction desired. So remember, we might have to flip 1 or so reactions around so that the reactants would cancel. If we're trying to get the reaction for diamond changing to graphite, we would need to have the diamond as a reactant, the graphite as a product. So we have to flip the second elementary step around. Notice here the CO2 cancels with the CO2 here. The oxygen cancels with the oxygen here, and that leaves us with this reaction here. So once you do that, remember, if you flip this reaction, you change the sign of your thermodynamic value here, the free energy. So we made this positive, and so now you add these numbers together, and you will get negative 3 kilojoules. So this is going to release 3 kilojoules of energy, and since this is negative, that indicates it's a spontaneous process, though it's not releasing a whole lot of energy. Delta H, delta S, and delta G, and how they're related to spontaneity. Remember, delta H is enthalpy. As I mentioned earlier, the temperature has to be in Kelvin. Now, if you look at this, this is kind of comparing the values for each of the thermodynamic factors that we've been looking at and how they have to do with spontaneity. You might want to pause this part of the video so you can get this copied in. But if your value for delta H is negative and the value for the T delta S here is positive, then that's going to give you a negative delta G value, which would indicate that it's spontaneous. If your delta G is negative, it's definitely a spontaneous process. If your value for delta H is positive, remember that's endothermic, and your value for the T times the delta S is negative, then that would give you a positive delta G value. That would indicate non-spontaneous reaction. So if your delta G is ever negative, that is how you tell for 100% sure that it's spontaneous. It means it's releasing energy. So if its delta G is positive, that means that it is a non-spontaneous process. So you really have to take into account the delta H and the delta S in order to determine if a process is going to be spontaneous for sure. If your delta G value, when you use this formula, if it is ever negative, you know for sure that it's spontaneous. Now, if these are both negative or if they're both positive, the value for delta G is really going to depend on if it's high temperatures or low temperatures. So it's going to be spontaneous, so it'll be negative. If the absolute value of delta H is greater than the absolute value of T delta S, the temperature has to be taken into account more. And that's only going to be true at very cold temperatures. Now, it will be spontaneous if the absolute value of T delta S is greater than the absolute value of delta H at very high temperatures. So like if both of these are positive. So it would make a bigger impact at low temperatures than it would at high temperatures. We will again do some calculations after break with that formula. All right, the third method of calculating the free energy is using the standard free energy of formation formula, and this should look familiar at this point. Again, the summation formula is what I call it. So it's exactly like the delta H, the standard enthalpy of formation, and the standard entropy of formation formula that we looked at, except it has the free energy here. So you would plug in your free energy values. It's products minus reactants. And one thing you'll notice on your thermodynamic tables is that the free energy of an element in its standard state is always going to be 0. That's something you'll notice off of your charts, though, when you look on your thermodynamic tables. All right, this next slide is going to look at the dependence on free energy and pressure when you talk about gases. Enthalpy is not pressure dependent, so your heat content does not depend on pressure. Entropy depends on volume, so it also depends on pressure. So we're talking about entropy, your disorder, because if you think about if you compress a gas, the volume is changing, so you're going to push the particles closer together, so they will have a higher order, so a lower entropy. Large volumes, remember, have entropy that is greater than small volumes because you're pushing the particles together. So entropy does depend on pressure, enthalpy does not. The entropy or disorder at low pressure is going to be greater than the entropy at high pressure. Free energy and equilibrium, how are they related? Well, equilibrium, remember, that point occurs at the lowest free energy value available. Equilibrium is very desirable. At equilibrium, the change in free energy is equal to 0. So once you get to equilibrium, delta G is equal to 0. And that's when your Q equals your K. Remember, Q was your reaction quotient when you apply your initial values of your pressures or concentrations, and then K represents the equilibrium constant. So delta G equals 0 means the K is equal to 1. So when your concentration of products equal the concentration of the reactants, it's at equilibrium. I did not mean to do that. All right. Delta G less than 0 means your K is greater than 1, and delta G greater than 0, so positive, means your K is less than 1. So that's when the reactants will be favored. Our last couple of slides here is calculating delta G when it's non-standard conditions. And again, we will do calculations with this if you just for now will get the formula down. Delta G at non-standard conditions, notice there's no degree sign here. It's equal to the delta G at standard conditions plus RT times the natural log of Q, which is your reaction quotient. Again, the products of reactants at initial conditions. Your R and your T has to be in Kelvin, and the R that we use here is going to be the 0.08206. The maximum possible useful work attainable from a process at constant temperature and pressure is equal to the change in the free energy. The amount of work actually obtained is always less than the maximum possible. All right, that's the end of this lesson. See you after break, and we'll work through these problems. Thanks so much for your patience and hard work, class.